The Solar System is the gravitationally bound system of the Sun and the objects that orbit it. It formed 4.6 billion years ago from the gravitational collapse of a giant interstellar molecular cloud. The vast majority of the system's mass is in the Sun, with most of the remaining mass contained in the planet Jupiter. The four inner system planets Mercury, Venus, Earth, and Mars are terrestrial planets, being composed primarily of rock and metal. The four giant planets of the outer system are substantially larger and more massive than the terrestrials. The two largest, Jupiter and Saturn, are gas giants, being composed mainly of hydrogen and helium. The next two, Uranus and Neptune, are ice giants, being composed mostly of volatile substances with relatively high melting points compared with hydrogen and helium, such as water, ammonia, and methane. All 8 planets have nearly circular orbits that lie near the plane of Earth's orbit, called the ecliptic. There are an unknown number of smaller dwarf planets and innumerable small solar system bodies orbiting the Sun. 6 of the major planets, the 6 largest possible dwarf planets, and many of the smaller bodies are orbited by natural satellites, commonly called moons after Earth's moon. 2 natural satellites, Jupiter's moon Ganymede and Saturn's moon Titan, are larger but not more massive than Mercury, the smallest terrestrial planet, and Jupiter's moon Callisto is nearly as large. Each of the giant planets and some smaller bodies are encircled by planetary rings of ice, dust, and moonlets. The asteroid belt, which lies between the orbits of Mars and Jupiter, contains objects composed of rock, metal, and ice. Beyond Neptune's orbit lie the Kuiper belt and scattered disk, which are populations of objects composed mostly of ice and rock. In the outer reaches of the Solar System lies a class of minor planets called detached objects. There is considerable debate as to how many such objects there will prove to be. Some of these objects are large enough to have rounded under their own gravity and thus to be categorized as dwarf planets. Astronomers generally accept about 9 objects as dwarf planets: the asteroid series, the Kuiper belt objects Pluto, Orcus, Haumea, Quaoar, and Make, and the scattered disk objects Gong, Eris, and Sedna. Various small body populations, including comets, centaurs, and interplanetary dust clouds, freely travel between the regions of the Solar System. The solar wind, a stream of charged particles flowing outwards from the Sun, creates a bubble-like region of interplanetary medium in the interstellar medium known as the heliosphere. The heliopause is the point at which pressure from the solar wind is equal to the opposing pressure of the interstellar medium. It extends out to the edge of the scattered disk. The Oort cloud, which is thought to be the source for long-period comets, may also exist at a distance roughly 1,000 times further than the heliosphere. The Solar System is located 26,000 light-years from the center of the Milky Way galaxy in the Orion Arm, which contains most of the visible stars in the night sky. The nearest stars are within the so-called local bubble, with the closest, Proxima Centauri, at 4.2441 light-years. Formation and evolution. The Solar System formed 4.568 billion years ago from the gravitational collapse of a region within a large molecular cloud. This initial cloud was likely several light-years across and probably birthed several stars. As is typical of molecular clouds, this one consisted mostly of hydrogen, with some helium, and small amounts of heavier elements fused by previous generations of stars. As the region that would become the Solar System, known as the pre-solar nebula, collapsed, conservation of angular momentum caused it to rotate faster. The center, where most of the mass collected, became increasingly hotter than the surrounding disk. As the contracting nebula rotated faster, it began to flatten into a protoplanetary disk with a diameter of roughly 200 O and a hot, dense protostar at the center. The planets formed by accretion from this disk, in which dust and gas gravitationally attracted each other, coalescing to form ever larger bodies. Hundreds of protoplanets may have existed in the early solar system, but they either merged or were destroyed or ejected, leaving the planets, dwarf planets, and leftover minor bodies. Due to their higher boiling points, only metals and silicates could exist in solid form in the warm inner solar system close to the Sun, and these would eventually form the rocky planets of Mercury, Venus, Earth, and Mars. Because metallic elements only comprised a very small fraction of the solar nebula, the terrestrial planets could not grow very large. The giant planets formed further out, beyond the frost line, the point between the orbits of Mars and Jupiter where material is cool enough for volatile icy compounds to remain solid. The ices that formed these planets were more plentiful than the metals and silicates that formed the terrestrial inner planets, allowing them to grow massive enough to capture large atmospheres of hydrogen and helium, the lightest and most abundant elements. Leftover debris that never became planets congregated in regions such as the asteroid belt, Kuiper belt, and Oort cloud. The NICE model is an explanation for the creation of these regions and how the outer planets could have formed in different positions and migrated to their current orbits through various gravitational interactions. Within 50 million years, the pressure and density of hydrogen in the center of the protostar became great enough for it to begin thermonuclear fusion. The temperature, reaction rate, pressure, and density increased until hydrostatic equilibrium was achieved, the thermal pressure counterbalancing the force of gravity. At this point, the Sun became a main sequence star. The main sequence phase, from beginning to end, will last about 10 billion years for the Sun compared to around 2 billion years for all other phases of the Sun's pre-remnant life combined. Solar wind from the Sun created the heliosphere and swept away the remaining gas and dust from the protoplanetary disk into interstellar space. As helium accumulates at its core, the Sun is growing brighter. Early in its main sequence life, its brightness was 70% that of what it is today. The solar system will remain roughly as it is known today until the hydrogen in the core of the Sun has been entirely converted to helium, which will occur roughly 5 billion years from now. This will mark the end of the Sun's main sequence life. At that time, the core of the Sun will contract with hydrogen fusion occurring along a shell surrounding the inert helium, and the energy output will be greater than at present. The outer layers of the Sun will expand to roughly 260 times its current diameter, and the Sun will become a red giant. Because of its increased surface area, the surface of the Sun will be cooler at its coolest than it is on the main sequence. The expanding Sun is expected to vaporize Mercury as well as Venus, and render Earth uninhabitable. Eventually, the core will be hot enough for helium fusion. The Sun will burn helium for a fraction of the time it burned hydrogen in the core. The Sun is not massive enough to commence the fusion of heavier elements, and nuclear reactions in the core will dwindle. Its outer layers will be ejected into space, leaving behind a dense white dwarf, half the original mass of the Sun but only the size of Earth. The ejected outer layers will form what is known as a planetary nebula, returning some of the material that formed the Sun but now enriched with heavier elements like carbon to the interstellar medium. Structure and composition. The word solar means pertaining to the Sun, which is derived from the Latin word sol, meaning Sunday. The Sun is the dominant gravitational member of the solar system, and its planetary system is maintained in a relatively stable, slowly evolving state by following isolated, gravitationally bound orbits around the Sunday. Orbits. The planets and other large objects in orbit around the Sun lie near the plane of Earth's orbit, known as the ecliptic. Smaller icy objects such as comets frequently orbit at significantly greater angles to this plane. Most of the planets in the solar system have secondary systems of their own, being orbited by natural satellites called moons. Many of the largest natural satellites are in synchronous rotation, with one face permanently turned toward their parent. The 4 giant planets have planetary rings, thin bands of tiny particles that orbit them in unison. As a result of the formation of the solar system, planets and most other objects orbit the Sun in the same direction that the Sun is rotating. That is, counterclockwise, as viewed from above Earth's North Pole. There are exceptions, such as Halley's Comet. Most of the larger moons orbit their planets in prograde direction, matching the planetary rotation. Neptune's moon Triton is the largest to orbit in the opposite, retrograde manner. Most larger objects rotate around their own axes in the prograde direction relative to their orbit, though the rotation of Venus is retrograde. To a good first approximation, Kepler's laws of planetary motion describe the orbits of objects about the Sunday. 433-437. These laws stipulate that each object travels along an ellipse with the Sun at one focus, which causes the body's distance from the Sun to vary over the course of its year. A body's closest approach to the Sun is called its perihelion, whereas its most distant point from the Sun is called its aphelion. 9 to 6. The orbits of the planets are nearly circular, but many comets, asteroids, and Kuiper belt objects follow highly elliptical orbits. Kepler's laws only account for the influence of the Sun's gravity upon an orbiting body, not the gravitational pulls of different bodies upon each other. On a human time scale, these additional perturbations can be accounted for using numerical models, 9 to 6. But the planetary system can change chaotically over billions of years. The angular momentum of the solar system is a measure of the total amount of orbital and rotational momentum possessed by all its moving components. Although the Sun dominates the system by mass, it accounts for only about 2% of the angular momentum. The planets, dominated by Jupiter, account for most of the rest of the angular momentum due to the combination of their mass, orbit, and distance from the Sun, with a possibly significant contribution from comets. Composition. The overall structure of the charted regions of the Solar System consists of the Sun, 4 smaller inner planets surrounded by a belt of mostly rocky asteroids, and 4 giant planets surrounded by the Kuiper belt of mostly icy objects. Astronomers sometimes informally divide this structure into separate regions. The inner solar system includes the 4 terrestrial planets and the asteroid belt. The outer solar system is beyond the asteroids, including the 4 giant planets. Since the discovery of the Kuiper belt, the outermost parts of the solar system are considered a distinct region consisting of the objects beyond Neptune. The principal component of the solar system is the Sun, a low-mass star that contains 99.86% of the system's known mass and dominates it gravitationally. The Sun's 4 largest orbiting bodies, the giant planets, account for 99% of the remaining mass, with Jupiter and Saturn together comprising more than 90%. The remaining objects of the Solar System together comprise less than 0.002% of the Solar System's total mass. The Sun is composed of roughly 98% hydrogen and helium, as are Jupiter and Saturn. A composition gradient exists in the Solar System, created by heat and light pressure from the early Sun. Those objects closer to the Sun, which are more affected by heat and light pressure, are composed of elements with high melting points. Objects farther from the Sun are composed largely of materials with lower melting points. The boundary in the Solar System beyond which those volatile substances could coalesce is known as the frost line, and it lies at roughly 5 times the Earth's distance from the Sun. The objects of the inner Solar System are composed mostly of rocky materials, such as silicates, iron, or nickel. Jupiter and Saturn are composed mainly of gases with extremely low melting points and high vapor pressure, such as hydrogen, helium, and neon. Ices, like water, methane, ammonia, hydrogen sulfide, and carbon dioxide, have melting points up to a few hundred kelvins. They can be found as ices, liquids, or gases in various places in the Solar System. Icy substances comprise the majority of the satellites of the giant planets, as well as most of Uranus and Neptune and the numerous small objects that lie beyond Neptune's orbit. Together, gases and ices are referred to as volatiles. Distances and scales. The astronomical unit would be the distance from the Earth to the Sun if the planet's orbit were perfectly circular. For comparison, the radius of the Sun is 0.00470. Thus, the Sun occupies 0.00001% of the volume of a sphere with a radius the size of Earth's orbit, whereas Earth's volume is roughly 1/millionth that of the Sunday. Jupiter, the largest planet, is 5.2 astronomical units from the Sun and has a radius of 71,000 kilometers, whereas the most distant planet, Neptune, is 30 from the Sunday with a few exceptions. The farther a planet or belt is from the Sun, the larger the distance between its orbit and the orbit of the next nearer object to the Sunday. For example, Venus is approximately 0.330 farther out from the Sun than Mercury, whereas Saturn is 4.30 out from Jupiter, and Neptune lies 10.50 out from Uranus. Attempts have been made to determine a relationship between these orbital distances, like the Titius-Bode law and Johannes Kepler's model based on the Platonic solids, but ongoing discoveries have invalidated these hypotheses. Some solar system models attempt to convey the relative scales involved in the solar system on human terms. Some are small in scale whereas others extend across cities or regional areas. The largest such scale model, the Sweden solar system, uses the 1/10-meter Avicii Arena in Stockholm as its substitute sun, and, following the scale, Jupiter is a 7.5-meter sphere at Stockholm Arlanda Airport, 40 kilometers away, whereas the farthest current object, Sedna, is a 10-centimeter sphere in Luleå, 912 kilometers away. If the Sun-Neptune distance is scaled to 100 meters, then the Sun would be about 3 centimeters in diameter, the giant planets would be all smaller than about 3 millimeters, and Earth's diameter along with that of the other terrestrial planets would be smaller than a flea at this scale. Sun. The Sun is the solar system star and by far its most massive component. Its large mass, which comprises 99.86% of all the mass in the solar system, produces temperatures and densities in its core high enough to sustain nuclear fusion of hydrogen into helium. This releases an enormous amount of energy, mostly radiated into space as electromagnetic radiation peaking in visible light. Because the Sun fuses hydrogen into helium at its core, it is a main sequence star. More specifically, it is a G2 type main sequence star, where the type designation refers to its effective temperature. Hotter main sequence stars are more luminous. The Sun's temperature is intermediate between that of the hottest stars and that of the coolest stars. Stars brighter and hotter than the Sun are rare, whereas substantially dimmer and cooler stars, known as red dwarfs, make up about 75% of the stars in the Milky Way. The Sun is a population I star. It has a higher abundance of elements heavier than hydrogen and helium than the older population II stars. Elements heavier than hydrogen and helium were formed in the cores of ancient and exploding stars, so the first generation of stars had to die before the universe could be enriched with these atoms. The oldest stars contain few metals, whereas stars born later have more. This higher metallicity is thought to have been crucial to the Sun's development of a planetary system because the planets form from the accretion of metals. Environment and habitability. Outside of the main part of the Sun's atmosphere extends the heliosphere and dominates the solar planetary system. The vast majority of the heliosphere is occupied by a near vacuum known as the interplanetary medium. Along with light, the Sun radiates a continuous stream of charged particles called the solar wind. This stream of particles spreads outwards at speeds from 900,000 km per hour to 2,880,000 km per hour, creating a tenuous atmosphere that permeates the interplanetary medium out to at least 100 O. Activity on the Sun's surface, such as solar flares and coronal mass ejections, disturbs the heliosphere, creating space weather and causing geomagnetic storms. The largest structure within the heliosphere is the heliospheric current sheet, a spiral form created by the actions of the Sun's rotating magnetic field on the interplanetary medium. Earth's magnetic field stops its atmosphere from being stripped away by the solar wind. Venus and Mars do not have magnetic fields, and as a result the solar wind is causing their atmospheres to gradually bleed away into space. Coronal mass ejections and similar events blow a magnetic field and huge quantities of material from the surface of the Sunday. The interaction of this magnetic field and material with Earth's magnetic field funnels charged particles into Earth's upper atmosphere, where its interactions create aurorae seen near the magnetic poles. The heliosphere and planetary magnetic fields partially shield the solar system from high-energy interstellar particles called cosmic rays. The density of cosmic rays in the interstellar medium and the strength of the Sun's magnetic field change on very long timescales, so the level of cosmic ray penetration in the solar system varies, though by how much is unknown. The interplanetary medium is home to at least two disk-like regions of cosmic dust. The first, the zodiacal dust cloud, lies in the inner solar system and causes the zodiacal light. It may have been formed by collisions within the asteroid belt brought on by gravitational interactions with the planets. A more recent proposed origin is the planet Mars. The second dust cloud extends from about 10O to about 40O, and was probably created by collisions within the Kuiper belt. The zone of habitability of the solar system is located in the inner solar system. Beside the solar conditions for habitability on solar system objects such as Earth, habitability might be possibly in subsurface oceans of various outer solar system moons. Inner solar system. The inner solar system is the region comprising the terrestrial planets and the asteroid belt. Composed mainly of silicates and metals, the objects of the inner solar system are relatively close to the Sun. The radius of this entire region is less than the distance between the orbits of Jupiter and Saturn. This region is also within the frost line, which is a little less than 5O from the Sunday. Inner planets. The four terrestrial or inner planets have dense, rocky compositions, few or no moons, and no ring systems. They are composed largely of refractory minerals such as the silicates which form their crusts and mantles, and metals such as iron and nickel which form their cores. 3 of the 4 inner planets have atmospheres substantial enough to generate weather. All have impact craters and tectonic surface features, such as rift valleys and volcanoes. The term inner planet should not be confused with inferior planet, which designates those planets that are closer to the Sun than Earth is. Mercury, Venus, Earth, Mars. Asteroid belt. Asteroids except for the largest, Ceres, are classified as small solar system bodies and are composed mainly of refractory rocky and metallic minerals, with some ice. They range from a few meters to hundreds of kilometers in size. Asteroids smaller than 1 meter are usually called meteoroids and micrometeoroids, with the exact division between the two categories being debated over the years. As of 2017, the IAU designates asteroids having diameter between about 30 micrometers and 1 meter as micrometeoroids, and terms smaller particles dust. The asteroid belt occupies the orbit between Mars and Jupiter, between 2.3 and 3.30 from the Sunday. It is thought to be remnants from the solar system's formation that failed to coalesce because of the gravitational interference of Jupiter. The asteroid belt contains tens of thousands, possibly millions, of objects over 1 kilometer in diameter. Despite this, the total mass of the asteroid belt is unlikely to be more than 1,000th of that of Earth. The asteroid belt is very sparsely populated. Spacecraft routinely pass through without incident. Ceres, Pallas and Vesta. Asteroid groups. Outer Solar System. The outer region of the Solar System is home to the giant planets and their large moons. The Centaurs and many short-period comets also orbit in this region. Due to their greater distance from the Sun, the solid objects in the outer solar system contain a higher proportion of volatiles, such as water, ammonia, and methane than those of the inner solar system because the lower temperatures allow these compounds to remain solid. Outer planets. The 4 outer planets, also called giant planets or Jovian planets, collectively make up 99% of the mass known to orbit the Sunday. Jupiter and Saturn are together more than 400 times the mass of Earth and consist overwhelmingly of the gases hydrogen and helium, hence their designation as gas giants. Uranus and Neptune are far less massive, less than 20 Earth masses each, and are composed primarily of ices. For these reasons, some astronomers suggest they belong in their own category, ice giants. All 4 giant planets have rings, although only Saturn's ring system is easily observed from Earth. The term superior planet designates planets outside Earth's orbit and thus includes both the outer planets and Mars. The ring moon systems of Jupiter, Saturn, and Uranus are like miniature versions of the solar system. That of Neptune is significantly different, having been disrupted by the capture of its largest moon Triton. Jupiter, Saturn, Uranus, Neptune. Centaurs. The centaurs are icy comet-like bodies whose orbits have semi-major axes greater than Jupiter's, and less than Neptune's. The largest known centaur, 10,199 Chariklo, has a diameter of about 250 kilometers. The first centaur discovered, 2060 Chiron, has also been classified as a comet because it develops a coma just as comets do when they approach the Sunday. Comets. Comets are small solar system bodies, typically only a few kilometers across, composed largely of volatile ices. They have highly eccentric orbits, generally a perihelion within the orbits of the inner planets and an aphelion far beyond Pluto. When a comet enters the inner solar system, its proximity to the Sun causes its icy surface to sublimate and ionise, creating a coma, a long tail of gas and dust often visible to the naked eye. Short-period comets have orbits lasting less than 200 years. Long-period comets have orbits lasting thousands of years. Short-period comets are thought to originate in the Kuiper belt, whereas long-period comets, such as Hale-Bopp, are thought to originate in the Oort cloud. Many comet groups, such as the Kreutz-Sungrasers, formed from the breakup of a single parent. Some comets with hyperbolic orbits may originate outside the solar system, but determining their precise orbits is difficult. Old comets whose volatiles have mostly been driven out by solar warming are often categorized as asteroids. Trans-Neptunian region. Inside the orbit of Neptune is the planetary region of the solar system. Beyond the orbit of Neptune lies the area of the trans-Neptunian region, with the donut-shaped Kuiper belt, home of Pluto and several other dwarf planets, and an overlapping disk of scattered objects, which is tilted toward the plane of the solar system and reaches much further out than the Kuiper belt. The entire region is still largely unexplored. It appears to consist overwhelmingly of many thousands of small worlds, the largest having a diameter only a fifth that of Earth and a mass far smaller than that of the Moon, composed mainly of rock and ice. This region is sometimes described as the third zone of the solar system, enclosing the inner and the outer solar system. Kuiper belt. The Kuiper belt is a great ring of debris similar to the asteroid belt, but consisting mainly of objects composed primarily of ice. It extends between 30 and 50 O from the Sunday. It is composed mainly of small solar system bodies, although the largest few are probably large enough to be dwarf planets. There are estimated to be over 100,000 Kuiper belt objects with a diameter greater than 50 kilometers, but the total mass of the Kuiper belt is thought to be only a tenth or even 100th the mass of Earth. Many Kuiper belt objects have multiple satellites, and most have orbits that take them outside the plane of the ecliptic. The Kuiper belt can be roughly divided into the classical belt and the resonant trans-Neptunian objects. The latter have orbits whose periods are in a simple ratio to that of Neptune, for example, going around the Sun twice for every 3 times that Neptune does, or once for every 2. The classical belt consists of objects having no resonance with Neptune, and extends from roughly 39.4 to 47.70. Members of the classical Kuiper belt are sometimes called cubewanos, after the first of their kind to be discovered, originally designated 1992 QB1, they are still in near primordial, low eccentricity orbits. Pluto and Charon. Others. Scattered disk. The scattered disk, which overlaps the Kuiper belt but extends out to near 500 O, is thought to be the source of short-period comets. Scattered disk objects are believed to have been perturbed into erratic orbits by the gravitational influence of Neptune's early outward migration. Most scattered disk objects have perihelia within the Kuiper belt but aphelia far beyond it. SDO's orbits can also be inclined up to 46.8 degrees from the ecliptic plane. Some astronomers consider the scattered disk to be merely another region of the Kuiper belt and describe scattered disk objects as scattered Kuiper belt objects. Some astronomers also classify centaurs as inward scattered Kuiper belt objects along with the outward scattered residents of the scattered disk. Eris and Gong Gong. Farthest regions. The point at which the solar system ends and interstellar space begins is not precisely defined because its outer boundaries are shaped by 2 forces, the solar wind and the Sun's gravity. The limit of the solar wind's influence is roughly 4 times Pluto's distance from the Sun. This heliopause, the outer boundary of the heliosphere, is considered the beginning of the interstellar medium. The Sun's Hill sphere, the effective range of its gravitational dominance, is thought to extend up to 1,000 times farther and encompasses the hypothetical Oort cloud. Edge of the heliosphere. The Sun's stellar wind bubble, the heliosphere, a region of space dominated by the Sun, has its boundary at the termination shock, which is roughly 8100 O from the Sun upwind of the interstellar medium and roughly 200 O from the Sun downwind. Here the solar wind collides with the interstellar medium and dramatically slows, condenses, and becomes more turbulent, forming a great oval structure known as the heliosheath. This structure has been theorized to look and behave very much like a comet's tail, extending outward for a further 40 O on the upwind side but tailing many times that distance downwind. Evidence from the Cassini and Interstellar Boundary Explorer spacecraft has suggested that it is forced into a bubble shape by the constraining action of the interstellar magnetic field, but the actual shape remains unknown. The outer boundary of the heliosphere, the heliopause, is the point at which the solar wind finally terminates and is the beginning of interstellar space. Voyager 1 and Voyager 2 passed the termination shock and entered the heliosheath at 94 and 84 O from the Sun, respectively. Voyager 1 was reported to have crossed the heliopause in August 2012, and Voyager 2 in December 2018. The shape and form of the outer edge of the heliosphere is likely affected by the fluid dynamics of interactions with the interstellar medium as well as solar magnetic fields prevailing to the south. E.g., it is bluntly shaped with the northern hemisphere extending 9 O farther than the southern hemisphere. Beyond the heliopause, at around 230 O, lies the bow shock, a plasma wake left by the Sun as it travels through the Milky Way. Detached objects. Sedna is a large, reddish object with a gigantic, highly elliptical orbit that takes it from about 76 O at perihelion to 940 O at aphelion and takes 11,400 years to complete. Mike Brown, who discovered the object in 2003, asserts that it cannot be part of the scattered disk or the Kuiper belt because its perihelion is too distant to have been affected by Neptune's migration. He and other astronomers consider it to be the first in an entirely new population, sometimes termed distant detached objects, which also may include the Object 2000 CR105, which has a perihelion of 45 O, an aphelion of 415 O, and an orbital period of 3,420 years. Brown terms this population the inner Oort cloud because it may have formed through a similar process, although it is far closer to the Sunday. Sedna is very likely a dwarf planet, though its shape has yet to be determined. The second unequivocally detached object, with the perihelion farther than Sedna's at roughly 81°, is 2012 VP113, discovered in 2012. Its aphelion is only about half that of Sedna's, at 458°. Oort cloud. The Oort cloud is a hypothetical spherical cloud of up to 1 trillion icy objects that is thought to be the source for all long-period comets and to surround the Solar System at roughly 50,000°, from the Sun, and possibly to as far as 100,000°. It is thought to be composed of comets that were ejected from the inner Solar System by gravitational interactions with the outer planets. Oort cloud objects move very slowly, and can be perturbed by infrequent events, such as collisions, the gravitational effects of a passing star, or the galactic tide, the tidal force exerted by the Milky Way. Boundaries. Much of the Solar System is still unknown. The Sun's gravitational field is estimated to dominate the gravitational forces of surrounding stars out to about 2 light-years. Lower estimates for the radius of the Oort cloud, by contrast, do not place it farther than 50,000°. Most of the mass is orbiting in the region between 3,000 and 100,000°. Despite discoveries such as Sedna, the region between the Kuiper belt and the Oort cloud, an area tens of thousands of in radius, is still virtually unmapped. Learning about this region of space is difficult, because it depends upon inferences from those few objects whose orbits happen to be perturbed such that they fall closer to the Sun, and even then, detecting these objects has often been possible only when they happen to become bright enough to register as comets. Objects may yet be discovered in the Solar System's uncharted regions. The furthest known objects, such as Comet West, have aphelia around 70,000° from the Sunday. Galactic context. The Solar System is located in the Milky Way, a barred spiral galaxy with a diameter of about 100,000 light-years containing more than 100 billion stars. The Sun resides in one of the Milky Way's outer spiral arms, known as the Orion Cygnus arm or local spur. The Sun lies about 26,660 light-years from the galactic center, and its speed around the center of the Milky Way is about 220 km per second, so that it completes one revolution every 240 million years. This revolution is known as the Solar System's galactic year. The solar apex, the direction of the Sun's path through interstellar space, is near the constellation Hercules in the direction of the current location of the bright star Vega. The plane of the ecliptic lies at an angle of about 60 degrees to the galactic plane. The Solar System's location in the Milky Way is a factor in the evolutionary history of life on Earth. Its orbit is close to circular, and orbits near the Sun are at roughly the same speed as that of the spiral arms. Therefore, the Sun passes through arms only rarely. Because spiral arms are home to a far larger concentration of supernovae, gravitational instabilities, and radiation that could disrupt the Solar System, this has given Earth long periods of stability for life to evolve. However, the changing position of the Solar System relative to other parts of the Milky Way could explain periodic extinction events on Earth, according to the Shiva hypothesis or related theories. But this remains controversial. The Solar System lies well outside the star-crowded environs of the galactic center. Near the center, gravitational tugs from nearby stars could perturb bodies in the Oort cloud and send many comets into the inner Solar System, producing collisions with potentially catastrophic implications for life on Earth. The intense radiation of the galactic center could also interfere with the development of complex life. Stellar flybys that pass within 0.8 light-years of the Sun occur roughly once every 100,000 years. The closest well-measured approach was Scholz's star, which approached to 52 plus 2314 Cow of the Sun, some 70 plus 1510 Kia, likely passing through the outer Oort cloud. Celestial neighborhood. The Solar System is surrounded by the local interstellar cloud, although it is not clear if it is embedded in the local interstellar cloud or if it lies just outside the cloud's edge. Multiple other interstellar clouds also exist in the region within 300 light-years of the Sun, known as the local bubble. The latter feature is an hourglass-shaped cavity or superbubble in the interstellar medium roughly 300 light-years across. The bubble is suffused with high-temperature plasma, suggesting that it may be the product of several recent supernovae. The local bubble is a small superbubble compared to the neighboring wider Radcliffe wave and split linear structures, each of which are some thousands of light-years in length. All these structures are part of the Orion Arm, which contains most of the stars in the Milky Way that are visible to the unaided eye. The density of all matter in the local neighborhood is 0.097 plus or minus 0.013 mpc3. Within 10 light-years of the Sun there are relatively few stars, the closest being the triple star system Alpha Centauri, which is about 4.4 light-years away and may be in the local bubble's G cloud. Alpha Centauri A and B are a closely tied pair of Sun-like stars, whereas the closest star to Earth, the small red dwarf Proxima Centauri, orbits the pair at a distance of 0.2 light-year. In 2016, a potentially habitable exoplanet was found to be orbiting Proxima Centauri, called Proxima Centauri b, the closest confirmed exoplanet to the Sun. The next closest known fusors to the Sun are the red dwarfs Barnard's star, Wolf 359, and Lalande 21185. The nearest brown dwarfs belong to the binary Lumen 16 system, and the closest known rogue or free-floating planetary mass object at less than 10 Jupiter masses is the sub-brown dwarf WISE 08550714. Just beyond at 8.6 Li lies Sirius, the brightest star in Earth's night sky, with roughly twice the Sun's mass, orbited by the closest white dwarf to Earth, Sirius B. Other stars within 10 light-years are the binary red dwarf system Lewitton 726-8 and the solitary red dwarf Ross 154. The closest solitary Sun-like star to the Solar System is Tau Ceti at 11.9 light-years. It has roughly 80% of the Sun's mass but only about half of its luminosity. The nearest and unaided visible group of stars beyond the immediate celestial neighborhood is the Ursa Major moving group at roughly 80 light-years, which is within the local bubble, like the nearest as well as unaided visible star cluster the Hyades, which lie at its edge. The closest star-forming regions are the Corona Australis molecular cloud, the Rho Ophiuchi cloud complex and the Taurus molecular cloud. The latter lies just beyond the local bubble and is part of the Radcliffe wave. Comparison with extrasolar systems. Compared to many extrasolar systems, the Solar System stands out in lacking planets interior to the orbit of Mercury. The known Solar System also lacks super-Earths, planets between 1 and 10 times as massive as the Earth, although the hypothetical Planet 9, if it does exist, could be a super-Earth beyond the Solar System as we understand it today. Uncommonly, it has only small rocky planets and large gas giants. Elsewhere planets of intermediate size are typical both rocky and gas, so there is no gap as seen between the size of Earth and of Neptune. As many of these super-Earths are closer to their respective stars than Mercury is to the Sun, a hypothesis has arisen that all planetary systems start with many close-in planets, and that typically a sequence of their collisions causes consolidation of mass into few larger planets, but in case of the Solar System the collisions caused their destruction and ejection. The orbits of Solar System planets are nearly circular. Compared to other systems, they have smaller orbital eccentricity. Although there are attempts to explain it partly with a bias in the radial velocity detection method and partly with long interactions of a quite high number of planets, the exact causes remain undetermined. Humanity's perspective. humanity's knowledge of the solar system has grown incrementally over the centuries. Up to the late Middle Ages Renaissance, astronomers from Europe to India believed Earth to be stationary at the center of the universe and categorically different from the divine or ethereal objects that moved through the sky. Although the Greek philosopher Aristarchus of Samos had speculated on a heliocentric reordering of the cosmos, Nicolaus Copernicus was the first person known to have developed a mathematically predictive heliocentric system. Heliocentrism did not triumph immediately over geocentrism, but the work of Copernicus had its champions, notably Johannes Kepler. Using a heliocentric model that improved upon Copernicus by allowing orbits to be elliptical as well as circular, and the precise observational data of Tycho Brahe, Kepler produced the Rudolphine tables, which enabled accurate computations of the positions of the then-known planets. Pierre Gassendi used them to predict a transit of Mercury in 1631, and Jeremiah Horrocks did the same for a transit of Venus in 1639. This provided a strong vindication of heliocentrism and Kepler's elliptical orbits. In the 17th century, Galileo publicized the use of the telescope in astronomy. He and Simon Marius independently discovered that Jupiter had 4 satellites in orbit around it. Christian Huygens followed on from these observations by discovering Saturn's moon Titan and the shape of the rings of Saturn. In 1677, Edmund Halley observed a transit of Mercury across the Sun, leading him to realize that observations of the solar parallax of a planet could be used to trigonometrically determine the distances between Earth, Venus, and the Sunday. Halley's friend Isaac Newton, in his Magisterial Principia Mathematica of 1687, demonstrated that celestial bodies are not quintessentially different from earthly ones. The same laws of motion and of gravity apply on Earth and in the skies. 142 The term solar system entered the English language by 1704, when John Locke used it to refer to the Sun, planets, and comets. In 1705, Halley realized that repeated sightings of a comet were of the same object, returning regularly once every 75–76 years. This was the first evidence that anything other than the planets repeatedly orbited the Sun, though Seneca had theorized this about comets in the 1st century. Careful observations of the 1769 transit of Venus allowed astronomers to calculate the average Earth-Sun distance as 93,726,900 miles, only 0.8% greater than the modern value. Uranus, having occasionally been observed since antiquity, was recognized to be a planet orbiting beyond Saturn by 1783. In 1838, Friedrich Bessel successfully measured a stellar parallax, an apparent shift in the position of a star created by Earth's motion around the Sun, providing the first direct, experimental proof of heliocentrism. Neptune was identified as a planet some years later, in 1846, thanks to its gravitational pull causing a slight but detectable variation in the orbit of Uranus. In the 20th century, humans began their space exploration around the solar system, starting with placing telescopes in space. Since then, humans have landed on the Moon during the Apollo program. The Apollo 13 mission marked the furthest any human has been away from Earth at 400,171 kilometers. All 8 planets have been visited by space probes. The outer planets were first visited by the Voyager spacecraft, one of which is the furthest object made by humankind and the first in interstellar space. In addition, probes have also returned samples from comets and asteroids, as well as flown through the Sun's corona and made flybys of Kuiper belt objects. 6 of the planets have or had a dedicated orbiter.